Let's jump right in. Welcome back to The Explainer. Today, we're tackling one of the absolute wildest, most counterintuitive paradoxes in all of modern technology: why measuring a qubit actually destroys it. If you've been following the massive race to build quantum computers, you already know qubits are the fundamental building blocks of the future. But there is a huge, glaring catch to how they actually work. Now, you've probably heard the rumor that a qubit is just a fancier, supercharged computer bit, that you can easily peek at it whenever you want, read what's inside, and just keep on computing. Yeah, that's a total myth. The reality? Looking at a qubit doesn't read it. It completely wrecks it. And honestly, this creates a really fascinating curiosity gap. Because a qubit, while nobody is watching it, holds something so much richer than just a simple 0 or a 1. It holds this private, delicate blend of both at the exact same time. And the single most destructive thing you can possibly do to that blend is the one thing everyone naturally assumes is harmless: taking a glance at it. It's like the computational magic literally only survives in the dark. Every quantum engineer in the world has to face this brutal trade-off. See, the whole point of a qubit is that rich in-between state. That is where the actual heavy lifting of the computation happens. But the only way to get an answer out of the machine is to measure it. And measuring is a wrecking ball. You never actually get to see the beautiful, complex state you spent so much time building. You only get the rubble it leaves behind when you finally look. Getting your head around that one fact is the difference between thinking quantum computing is just regular computers but faster, and understanding what it truly is. Okay, let's break this down into 3 core ideas. Let's dive right into idea 1, the spinning coin. I want you to picture a coin spinning on a tabletop right in front of you, just whirling around. While it spins, ask yourself, is it heads or is it tails? The honest, literal answer is neither, and kind of both. It's this live, whirling thing that simply hasn't committed yet. The spin itself is the information. That right there, that is your qubit in its natural, unmeasured state. Now imagine just slamming your hand down on that live spinning coin. Wham, it freezes. Heads, done. But notice what actually just happened there. The spin is gone forever. It's not hidden under your hand. It didn't sneak off somewhere else. You forced a thing that was genuinely undecided to pick a side. And by forcing it, you completely erase the very motion that made it so interesting in the first place. In physics, that hand slamming down has a very specific name: collapse. Collapse is when the rich, leaning, spinning state of a qubit snaps instantly to a boring flat 0 or a flat 1 the second you measure it. You walk away with one outcome, heads or tails, 0 or 1, and you might get this smug feeling that you successfully read the qubit. But you didn't read the blend. You annihilated it, just to keep a single splinter. I actually want to slow down for a second and let this next thought really sink in. You're not a detective uncovering a truth. You're a judge handing down a sentence. It's not that the qubit was secretly a 0 all along and you finally caught it out. No, before you looked, there was literally no fact of the matter. The very act of looking is what created the answer. Okay, moving right along to idea 2, the weighted die. Let's see how this all builds together. If measurement doesn't reveal what the qubit really was, what does that leaning, spinning state actually do if it doesn't hold a fixed answer? Well, think of a qubit's state as an arrow that can point anywhere on a globe. If it points straight up to the North Pole, that means a solid 0. Straight down to the South Pole, solid 1. But the arrow is allowed to point anywhere in between, out over the equator, or slightly tilted up in the Northern Hemisphere. And here is the secret. Where the arrow points does not decide your final answer. It decides the odds of your answer. Think about it like this. If you tilt the arrow partway up north, you get a probability split. Let's say an 80% chance of a 0 and a 20% chance of a 1. If you point it dead north, sure, you get a 0 every single time. But tilted like this, you'll probably get a 0, say, 4 times out of 5. But 1 time out of 5, boom, it flips to a 1. And there is absolutely no way to predict which roll will be the 1. Reading a qubit isn't like reading a computer screen. It is exactly like rolling a weighted die. Now, what if you park the arrow right on the equator, exactly halfway between the poles? That yields a perfect coin flip, true 50-50. There's no skill involved, no hidden tell you can look for. It is completely, fundamentally random. But here is the incredibly cruel twist of quantum mechanics. You set the weighting, right? But you can never, ever directly see it. When an engineer prepares a qubit, they tilt the arrow exactly where they want it. They arrange the odds perfectly. But because looking destroys the setup, a single glance only ever gives you one face of the die, a flat 0 or a flat 1. To even estimate how you weighted it in the first place, you'd have to repair the exact same qubit thousands of times and tally the results, completely destroying it every single time. The true weighting is yours, it's totally real, but it is forever locked away from a single view. Now, I know what you're thinking. You're thinking this all sounds like a massive tragedy, right? A fragile technology ruined by the simple act of trying to use it. But let's flip that around. Let's jump into idea 3. The bug is a superpower. We're about to see how this incredibly fragile destructiveness is actually one of the most powerful security advantages humanity has ever discovered. Think about an ordinary classical letter. A spy can intercept it, carefully steam it open, take a photo, reseal it, and send it on its way. You receive it looking completely untouched, and the spying was entirely silent. No one knows. But quantum information, it literally cannot be copied silently. Because looking destroys the state, any eavesdropper who intercepts a stream of qubits to try and read them is forced to measure them. And measuring leaves huge, obvious, irreparable dents. So here is the beautifully simple logic of how a quantum cryptography alarm system actually works. Step 1. The eavesdropper intercepts the transmission and measures the qubits to try and spy on your message. Step 2. Because they looked, the qubits instantly collapse. The original carefully crafted odds are destroyed, leaving dents in the data. So the intercepted qubits that finally arrive to the receiver are now statistically wrong. Step 3, the sender and receiver just compare a handful of their numbers out loud over a normal channel. If the numbers line up perfectly, the channel was clean. But if they're scrambled, boom, someone was listening. You cannot spy on a qubit without leaving fingerprints. The bug is the feature. And guys, this matters so much because we aren't relying on some clever mathematical code that a supercomputer could eventually crack in 10 years. Unhackable communication here rests on an absolute, unbreakable law of physics. The destructiveness of measurement is exactly what rings the alarm. All right, let's bring it all home with the quantum reality check. Let's take a breath here. We've covered a ton of ground, so let's lock in exactly what you should take away from this explainer today. Number 1, collapse. Looking at the spinning coin forces it to commit and erases that spin forever. Number 2, the odds. The qubit's leaning doesn't hold a hidden secret answer. It sets the probabilities. They're weighted dice that you can arrange but never directly watch. And number 3, the superpower. That exact same destructiveness is what catches spies, making silent eavesdropping literally impossible. Which brings us to an even stranger door. You might be yelling at the screen right now, wait, if a spy can't look at the qubits without denting them, why don't they just clone the qubits first, send the originals along, and measure the copies in private? Well, that introduces the silent rule guarding the entire quantum internet, the No-Cloning Theorem. It is a fundamental law of physics stating it is completely forbidden to copy an unknown quantum state. Not because our tech isn't good enough yet, because the universe literally forbids it from happening.
But hey, we'll have to save the weird mechanics of cloning for another explainer. Until then, I'm leaving you with one provocative question to chew on. Of all the rules we hit today, which one bends your head the most? Is looking breaks it still the weirdest one? Or does the idea that you create the answer by looking out weird it for you? I genuinely want to know what you think. Thanks so much for learning with me today. And as always, keep questioning everything.